Hi everyone. My name is Eni Maria Binti Mahat, and I will be your moderator for today's webinar. So, on behalf of the Pejabat Timbalan Naib Chancellor Penyelidikan dan Inovasi TNCPI, it is my great pleasure to welcome all of you to the live research webinar series 2.0. So, before we move further, I would like to ask for your favor to please mute your microphone. Make sure your microphone is muted along the way to avoid any noise disturbance. So that we could have a very smooth and clear conversation throughout the session. If you have any question to the speaker, you can text us through the conversation message at the end of the session. Then I will read the questions on behalf of the reviewers. Okay, so for your information, this webinar is also available through our TNCBI FB Live. So please do like and follow our FB, Instagram, and Twitter at TNCPI_UITM. And please not forget at our YouTube, you can search for TNCPI UITM. So Dr. Sufri, apa khabar hari ini? How are you?
Alhamdulillah, Dr. Eni, sehat.
Work from home ke hari ini ke work from office?
At home.
At home. Okay, Dr. Supri, I think you are well already with us. So, but before that, allow me to share with all the reviewer about your background. Yeah, Doctor.
Yes, sure
Okay.
can proceed.
Okay, everyone. So Dr. Muhammad Sufri Mastuli is a senior lecturer of chemistry at the Faculty of Applied Sciences, FSG, University Technology Mara. And he is also a research fellow at Center for Functional Materials and Nanotechnology, Institute of Science, UITM. And Dr. Sufri obtained his PhD in 2019 in catalysis from University Putra, Malaysia. He holds Master of Science in Chemistry with distinction from University of Wollongong, Australia. He also holds a Bachelor of Science Honours in Applied Chemistry from the UITM. So Dr. Sufri has been working at UITM since January 2009, and so far he published about 40 articles in Scopus and WOS together with his research collaborators. He also secured about 22 research projects with a total of more than near to 1.3 million ringgit Malaysia from the international, national, and internal grants as the principal investigator as well as the researcher. So without further ado, I would like to welcome Dr. Muhammad Sufri Mastuli, who is a good friend of mine, to share his research findings in the topic of catalytic gasification of oil palm from biomass in supercritical water for syngas production. Silakan, Doktor.
Dr. Eni, thank you very much for the very kind introduction. Before I start, please allow me to share the slide of presentation. Yeah, I think I hope. Can you see my slide?
Yes.
Okay, thank you very much. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good evening, everyone. Again, I am Sufri, a senior lecturer from Faculty of Applied Sciences, and also a fellow researcher at Institute of Science, UIT, inshallah. First of all, I would like to thank very much to the Office of Research in Innovation of UITM for this great opportunity to share my research interests. For today's webinar, I would like to talk on the catalytic gasification of OPF biomass in supercritical water for the syngas production. Before I go more detail about the topics, again, allow me to explain briefly sorry, I think. Okay, allow me to explain my research area. As you can see on the slide, my research area is more on the catalysis and also on the biofuel. In my research group, we synthesize several types of catalysts, majorly metal oxide, support or dope, and also we synthesize the single atom alloy, nano catalyst, and also porous catalyst. We're using a different arranging type of synthesis method. It can be a solid state, decomposition, salt gel, precipitation, combustion, and also the hydrothermal. The synthesized catalyst will be tested in various type of reaction. First, trans esterification, hydroxy deoxygenation, deoxygenation reaction, and gasification reaction. So the expected product from the experimental is more to on the biofuel. We obtain the biodiesel, green fuel, the jet fuel, the green diesel, and also the hydrogen. So for today, I will focusing on the metal oxide catalyst, support and dope that synthesized using the combustion technique and also tested in the gasification reaction in order to produce the hydrogen. Okay. For the introduction, I will discuss briefly the background of research and also the research motivation. All right. Okay. According to the International Energy Outlook that published by the U.S. Energy Information and Administration, the world energy consumption is continuously increased from year to another year, and also it projected increasing even until a year of 2040. As you can see from this slide, Asia, the countries in Asia is projected to have largest energy consumption due to the population and economic growth, as well as the fast progress in the service and manufacturing sector to achieve the sophisticated living style. So, the energy sources either non-renewable. Most of the time, non-renewable is referring to the petroleum-based fuel, and also renewable, except for the coal, are projected to increase in terms of consumption. So, what is the problem with this increasing the energy consumption? So, the major concern is the utilization of non-renewable energy. Non-renewable energy, for example, we have petroleum and other liquid natural gas that we normally use in daily life, is responsible for the global warming, and also the climate change is a very, we have this problem every day. And also, it is associated with the oscillating. It means that is the changing the fuel price and also the uncertainty of the fuel reserves. So the energy paradigm is started to shift from non-renewable, from the petroleum base into the renewable source of energy. Okay. We know transportation is the major contributor for the carbon dioxide emission that the main factor for the global warming. Interestingly, from the report, the mixing or the combination between the use of non-renewable and also the renewable energy could reduce the CO2 emission for all the sectors. So the latest data on regarding the world energy scenario is also available in the annual energy outlook 2020 that published by the US Energy Information Administration. So for those researchers, students involved in the research energy area, so you can refer this report in order to assist to help you, okay, in your research studies. Okay, so since my research is more to hydrogen, so I explain a little bit on the hydrogen is the energy carrier. It's quite famous. The hydrogen can be used as the alternative energy carrier for the transportation sector due to the success of fuel cell technology. The hydrogen technology is very famous in Japan and also in Malaysia as well. We have bus using the hydrogen. I think the Sarawak the Negeri of Sarawak, I tried to start using the hydrogen is the fuel for their public transportation, mainly the bus. All right. So why we interested with the hydrogen? Because the hydrogen is a clean fuel. Is the combustion in the fuel cell is only produce water. It's meant that the product is water, so it's no CO2. All right. So this is the reason it's become famous nowadays. Another reason is the in terms of energy density. The hydrogen has the highest energy density is compared to the other type of the fuel or other type of energy. All right. So unfortunately, the hydrogen itself we cannot is not readily available in nature. We have to extract the hydrogen from somewhere. Okay, it cannot capture the energy from the air. Right. So the hydrogen can be produced from various resources, either non-renewable or renewable resources. As you can see on this diagram, conventionally we can have the hydrogen from natural gas, oil, coal. This is non-renewable resources. But researcher or industry has started to produce the hydrogen from another source like the biomass, nuclear, solar, and also wind source. Okay, so all these I call it all these resources will undergo different process, either gasification, electrolysis, it can be pyrolysis, and so on and so forth, in order to produce the hydrogen. Okay, I'm will focusing on the hydrogen produced from the biomass. Currently, hydrogen is mainly produced by steam reforming of natural gas or naphtha. This is a non-renewable. This is a petroleum-based resource due to the lower cost of production. The biomass has a great potential. It's a feedstock for the hydrogen production. It can reduce the dependency on the fossil fuel, and also it can meet the increase of the energy demands. Okay, so if we produce the hydrogen from the biomass, it can be renewable and it can be sustainable as a biofuel. So this is several example of biomass that are available widely. We have a corn, a wood, and also the sugarcane. This is lignocellulosic biomass. But in Malaysia or even in the Southeast Asian country, we are very famous with the oil palm. So oil palm biomass. For your information, each tree of the oil palm is only 10% expected is the oil. However, the 90% is remain is the biomass. So we have several types of biomass. We can have the frond, the pelepah. We can have the trunk, which is the batang pokok. We can have the bunches EFB after we pull out the palm fruit before we extract into the oil. We can have the fiber, but for this research, I will focusing the I will investigate the potential of OPF, oil palm frond is the feedstock for my hydrogen. Why I choose the OPF due to these two reasons. The first reason is the OPF is containing a higher amount of cellulose and hemicellulose and also a lower amount in terms of lignin. Another factor is in terms of availability. The OPF available greatly is compared to other solid waste biomass. For these two reasons, I decide, okay, I want to study the potential of the OPF. So, conversion the biomass is quite difficult. So, I use this latest technology. It's not called it latest. This is quite recent. We call it a supercritical water gasification. From the name, is the extension or is the modification of the gasification. Gasification is the conventional way to produce the gas from the biomass. But in this technology, we're gonna employ supercritical water is the reaction medium. What is the difference of supercritical water with the normal water that we have? The water in the supercritical stage is supposedly the water should be heated at higher, it above a critical point. This is the phase diagram of the water. So the water should be heated at 274 degrees C and also 20 to 1.1 megapascal. So the supercritical water gasification is a promising technology for the conversion of waste biomass into hydrogen. Remember, the biomass is normally containing huge amount of the moisture inside the biomass. This is the main problem. Okay, when we using the biomass is the feedstock. So this technology, we using the supercritical water is the reaction medium. So when we use the supercritical water, so we no need the free drying treatment for the biomass because the biomass we mix it with the supercritical water. However, in the conventional gasification, before we start the gasification reaction, the biomass has to be dry. Okay. So the supercritical water gasification of real biomass. Real biomass is made real feedstock, like the one that explained just now, the bagasse, the corn, or the biomass. It's more challenging is compared to the gasification of model compound. Model compound is we focus one type of chemicals like cellulose or hemicellulose or lignin. So the gasification of biomass is quite challenging because it's a mixture of a lot of things inside the biomass. It's a mixture of the cellulose, it's a mixture of the hemicellulose and also the lignin. So in order for us to convert this biomass into the simplest molecule, which is hydrogen, is a very tough. So, in general, the steam reforming reaction taking place during the reaction in producing a mixture of gas. So, in this reactor, steam reforming reaction will be occur and produce a mixture of gas. Bila kata mixture of gas is a combination of hydrogen, carbon monoxide, we have a carbon dioxide as well, and also we have a methane is the final product. This a mixture of gas, sometimes we call it a syngas. Syngas is a synthesis gas. So this is no need to. I don't think so. I want to explain this is a very detailed. But this is the chemical reaction for the steam reforming reaction. What you can observe this. This is the product. It contains hydrogen, CO, and also CO2 is the final product. In addition to the steam reforming reaction, during the supercritical water gasification, it also have intermediate reaction. The most famous intermediate reaction is water gas shift reaction, WGSR. So what is water gas shift reaction? The carbon monoxide that produced in situ during the reaction will be reacted with the supercritical water in order to increase further the total yield of the hydrogen. But in the same time, it produces the carbon dioxide as well. Another intermediate reaction is a methane reaction. The methane reaction is the a reaction to produce more methane. If the carbon monoxide in the reactor react with the produced hydrogen, it can produce more methane. Or if the CO2 produced react with the hydrogen, it also produce methane. So it means that if this methane reaction happen progressively, the amount of hydrogen will be reduced. Amount of methane will be increased. So it looks like if being hydrogen is our expected product, so we prefer the reaction should be progress actively water gas shift reaction instead of the methanation reaction. So either we want to on this reaction, to off this reaction, we should it on the catalyst. Okay. So the catalyst will be activated the water gas shift reaction, so we can have a higher amount of hydrogen. So hopefully the catalyst that we design, we testing will inactive for this reaction. So it can boost up the yield of the hydrogen. So these two reactions will be control the final product. Either the final product is the syngas rich with the hydrogen, or the final product is the syngas rich with the methane. So we have to control the properties of the catalyst. So since I'm interested on the hydrogen gases, so from the literature, the nickel-based catalyst widely reported is the heterogeneous catalyst to produce the hydrogen. The nickel-based catalyst, it can in a form of nickel metal, or it can be in a form of nickel oxide. This is the active component and can be supported onto different types of support. For example, we have alkaline metal oxide, and also we can have a transition metal oxide type of support, or some researcher focusing on the carbon-based support, activated carbon, and also CNT, carbon nanotube. Okay. The yield of the hydrogen that produced in the product can be further increased by using a promoter. So it's mean that we can it on another promoter. Normally, it's a transition method. Okay. In this study, this is my novelty. The novelty of my research. I tried to introduce another catalyst structure. Instead of using support type of catalyst, I introduced the group catalyst structure. So from my survey during that time, no literature reported on the supercritical water gasification using dope catalyst. But don't get me wrong, of course, the dope compounds like alloy is widely studied by other researchers, but it's not for this application, for other application. This is the characteristic of the catalyst. Every time we try to design, try to synthesize the catalyst, we have to think these three or these four things. The catalyst should be cheaper. The catalyst should be abundantly available. The most important part is this one. It should be active. It should be selective and should be stable, and it can be reusable. Okay, so the uh, the research was carried out during the research I want to talk today was carried out during my PhD in catalysis. Is Dr. Annie mentioned from the Faculty of Science at University Putra, Malaysia. All the findings or all the results written in the thesis have been published in Science Direct. So for today purposes, for today webinar series, I would like to focus to share the findings from one of the published article. It is the comparison between support in dope magnesium oxide catalyst in supercritical water gasification for hydrogen production. So after this is a more dry. After this is a bit difficult to understand, but I try my best to make it more linear in order the audience can understand what I'm doing. Okay. All right. For the objective of study, in this study, I'm synthesized and characterized two classes of catalysts: support catalyst and also dope catalyst. For the support catalyst, the active metal, the nickel oxide and also the zinc oxide will be supported onto the magnesium oxide. It's a catalyst support. For the dope catalyst, the active metal of nickel and zinc will be substitute or will be doping substitutionally ataupun will be inserted into the cubic structure of the magnesium oxide. I think from this diagram, you can differentiate what is the support catalyst, what is the dope catalyst. Next is the catalytic performance of the synthesized catalyst, the dope and also the supported in the dope were evaluated for the gasification of the OPF, the pelepah one, the pelepah sawit, in order to produce the hydrogen. Hopefully, it can be used in a car. Last but not least, the objective of the study, the relationship between the catalyst properties, the properties that we design, and the catalytic performance will be discussed in details. Okay, for the methodology, the support catalysts were synthesized using a conventional technique, impregnation method. The dope catalyst can be obtained using the combustion method. So the detail of the methodology, if you are interested to know, you can refer my published paper. But for this, we will not talk. I don't take to explain it in very detail. So the precursor that obtained from this two synthesis method calcine at 600 degrees C for 6 hours to give the expected catalyst that we want. So the catalyst form undergo a series of characterization technique. From the XRD, we have the BET, we have the VSEM, HR10, and also the XPS analysis. For the catalytic performance, we use the batch supercritical water gasification reactor. This is the schematic diagram of the reactor. The biomass, the OPF, will be it on together with the catalyst in this reactor. We top up with volume of water, and then we heat the reactor up to 400 degrees Celsius, 25 megapascal for 30 minutes. After we completed the reaction of 30 minutes, we stop the reaction. This valve will be open. The gas produced from the reaction will be flowed in and collected by using the sampling bottle. So the gas product that we collect will be analyzed by using gas chromatography. GC, we're using the GC-TCD and also the GC FID, right? So this batch reactor is fabricated by myself. I made it by my own during my research attachment at the Hiroshima University of Japan. Since my background is not engineering, fabrication the reactor is a tough of life, but saya gagahkan juga lah to make it complete. Okay, but Alhamdulillah, dengan pertolongan all the engineer and the researcher, I managed to fabricate the reactor by my own. So now we're moving forward on the results in discussion. First is the XRD. The support endocatalyst that synthesized in this study can be illustrated by using this diagram. I think most of you already understand what is the different support endo. Support the active metal on the top of or outside of the cubic of magnesium oxide. The dope, the active metal, the nickel and zinc, we try to insert it into the cubic structure of the magnesium oxide. So how do we know this catalyst form? So we are using XRD is another technique to confirm the formation of the catalyst. So the top one is the XRD result of the support catalyst. The below one is the XRD result of the dope catalyst. The support is SP, the dope is DP. As you can see from the XRD diffraction pattern, all the catalysts, the nickel SP, zinc SP, nickel dope, zinc dope, all the catalysts exhibited the XRD peaks of magnesium oxide because each catalyst they have magnesium oxide. So the magnesium oxide it should be appeared. in each catalyst. It indicated by the black dot. This is the MgO, 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 dan seterusnya. Okay. So another characteristic from the SRD pattern, the supported catalyst, it appeared is the mixed phase, is more than one phase because the active metal is outside. So supposedly it appeared in mixed phase. So for this nickel Sp, nickel oxide and magnesium oxide, the XRD is coincide each other, is overlap each other because the crystal structure of nickel oxide and magnesium oxide are similar. It's a cubic crystal structure. This why is coincide each other. However, this coincidence, the overlapping of the peak is not occur for the zinc oxide supported on the magnesium oxide because the zinc oxide is hexagonal, the magnesium oxide is cubic. So this is the indicator the supported catalyst can be obtained successfully. However, for the dope catalyst, since we see the diagram, the active metal is inserted in the cubic structure. This is why the nickel DP, the zinc DP produce a similar XRD pattern. Again, this show the dope catalyst can be obtained. This is mixed phase. This is the single phase. All right. From the fission images, the image that we obtained from the scanning electron microscopy, the supported catalysts have irregular shape of particle. For example, the nickel Sp is look like a freakish morphology. The zinc Sp is more to the spherical. Interestingly, when we change the structure from the support to the dope, the particle size are getting smaller and smaller until in that point we cannot differentiate the morphology. So we decide to further the analysis using the TEM, high resolution transmission electron microscopy. By using the HR10, it higher voltage, 200 kV, we can observe the small particle clearly. As we can see, the nickel DP, the zinc DP appeared in the spherical form with the particle size less 100 nanometer. So another finding, the dope catalyst, the particle also highly dispersed. Okay, highly dispersed. This is also important factor to be active in the catalytic reaction. This finding in agreement with the surface area from the BET analysis. The dope catalyst, the nickel DP, the zinc DP have a larger specific surface area than the supported catalyst. The smaller the particle, the larger the surface area. Regardless of support or dope, the zinc, regardless, kita tak kisah dia support or dope, the zinc is always lower in surface area. But later, when we see the catalytic reaction, surprisingly, the zinc-based catalyst is perform better compared to the nickel-based catalyst. Okay, so this figure is showing the nitrogen absorption, desorption isotherm and also the pore size distribution. It found that from the isotherm, the support catalysts are macroporous, type 4, and the dope catalyst appeared is mesoporous, type 2. From the BGH plot, we also found the dope catalyst have narrower, is quite narrow. The distribution of pore size is narrow compared to the pore size distribution of the support catalyst. And also, the volume of the pore, the dope catalyst produce a higher volume compared to the support catalyst structure. In addition, this is the schematic diagram that we expect. It is expected for the dope catalyst, the no pore, this is a pore, it look like a pore. I assume this is a pore. No pore blockages, no pore tripping by the active metal, because the active metal we insert in the crystal structure of the catalyst support. In this case, the magnesium oxide. Next is the TPD ammonia. The TPD ammonia is the analysis to determine the DCCT in terms of DCCT strength or in terms of the amount of basic active site. Is I red color, the dope catalyst, nickel DP and zinc DP, the amount of this basic active site very high in the medium basic strength. Medium basic strength is from 300 to 600 degrees Celsius, right? Okay, we moving forward to the catalytic performance. All the synthesized catalysts in this research were used to catalyze the supercritical water gasification of OPF biomass into the syngas. Remember, syngas is a mixture of gas, but we try our best to alleviate the yield of the hydrogen in the syngas. Without catalyst in here, without catalyst, the biomass of OPF also can be decomposed in the supercritical water, even at the low gasification temperature. All the catalysts that we studied are active for the water-Gischef reaction. If you still remember, the water-Gischef reaction is important and is inactive for the methanation reaction. Why we said so? If you observe closely, the yield of the hydrogen keep increasing. And the yield of the carbon monoxide, the pink color, is keep reducing. This is agreed with the water-Gischef reaction. However, the methanation reaction is not activated. This is why you observe the blue color, the methane yield is remain unchanged throughout the way different type of catalyst. So the catalyst that we reported is active for water-Gischef reaction, but it's not active for the methanation reaction. Okay, another information is we find out the dope catalyst. This diagram I changed it into another presentation so we can see it clearly. The yield of the hydrogen is kept increasing. The yield of other gases is reduced. So also we can see the dope catalyst, the nickel DP and zinc DP is perform better as compared to the nickel SP and also the zinc SP. The the zinc-based catalyst, let's say we don't care about the structure, support or dope, we find out the zinc always better than nickel. The zinc always better than the nickel. So it's meant that as a zinc is a good, is the active component to gasify the biomass to produce high amount of hydrogen yield. So why the zinc is better than the nickel? In literature, most of research is focusing on the surface area. But the surface area is not only the reason the catalysts are actively active in the reaction. They have another factor will influence the reactivity. If you still remember, the zinc has a lower surface area compared to the nickel, but in this case, we prove the zinc perform better. So what is the reason? Because the VCCT from TPD ammonia, the zinc exhibited greater amount of basic active strength, the medium strength compared to the nickel DP and also nickel SP. So surface area plus VCCT properties is the extra advantage for the active catalytic reaction. It's reported in the literature the basic catalyst can promote the water gas reaction, can promote this reaction. It can increase the CO2 adsorption capacity and also it can reduce the terry compound. Why reduce the terry compound? Because the gasification by using the biomass, the tar is the major problem when we using the gasification technique. So before the last part, I think I try to discuss the catalyst stability by using XPS measurement, because when we change the structure from support to dope, we expected the stability also improve. So this is the XPS result. Okay. The BE value, the binding energy, normally used to determine the stability of the catalyst structure. So from left to right, the binding energy increase. When we analyze the result carefully, we find out the catalyst stability can be arranged in this order, depending on the BE value. So the zinc DP is the most stable compared to the zinc SP. And the nickel catalyst is the less stability in terms of the structure stability. All right. The detail of the valence, the detail of the binding energy values are given on the next slide. All right. So I think it's quite it's quite a lot already. I come with the conclusion. We can conclude that the syngas rich with the hydrogen also can be produced from our local biomass oil palm by using the supercritical water gasification, even though it lower gasification temperature 400 degrees C. And the dope catalyst structure exhibited a higher amount of hydrogen yield is compared to the supported catalyst. And also, we find out the zinc base more active in the reaction for the hydrogen production is compared to the nickel base catalyst. We say the catalytic performance is not only depending on the surface area, it can be influenced by the basicity, the amount, and also the strength, and also it can be influenced by the stability. The dope catalyst the dope structure main serve is the new catalyst structure system for this supercritical water gasification reaction. So our novelty in this study, we try to shift the thinking from the support type of catalyst into the dope catalyst. All right. Okay. For this opportunity, I'm also take this opportunity to give a special thanks to these three professor. The first professor is Professor Dr. Taufik Yap, is my former supervisor during the PhD study. Currently, he is the Vice Chancellor of University Malaysia Sabah. And these two lady, Professor Dr. Nolida Kamarul Zaman, she's already retired 2 years ago. And also Professor Dr. Nur Hadayani Ismail. These two tough lady is my mentor and to keep me doing research, and research. They always remind me research, and research. Okay, last, I would like to give the acknowledgement to Professor Dr. Farida Zuraina Muhammad Yusuf, a Dean of Faculty of Applied Sciences, UITM Shah Alam. Also goes to the Professor Dr. Zurina Shamiri, Director of Institute of Science, UITM, Associate Professor Dr. Zoraida Kostaimi, Deputy Director, and also my head of center, the head of the Center for Functional Material and Nanotechnology, Professor Dr. Muhammad Rusuk Mahmud. In last, my former head of center during my center nanomaterial research, Professor Dr. Rihanum Yahya Suban, also going to retire soon. And my heart goes to the my big family, the Center for Nanomaterial Research, the researcher, the lecturer, the supporting staff, the students. This center is no longer existing, has changed to, is rebranding to another new center, a Center for Functional Material and Nanotechnology. It's a new family hit by Professor Rousseau. Thank you very much to all these research group. Last but not least is my postgraduate students. So for our future collaboration, any researcher, any lecturer, any student would like to discuss further. It's not about hydrogen, maybe other technical instrumentation and so on and so forth. You can contact me by using WhatsApp. Just introduce yourself. Inshallah, I will reply. Or you email me to the UITM email, or you email me to the Yahoo email. I said so. Thank you very much for your attention. I think it's enough for today. Dr. Annie, I return this webinar series to you.
Okay. Thank you, Dr. Sufri. It's very informative sharing session with you. So I would like to ask for your permission. So may we go for the Q&A session, Doctor?
Yeah, sure can.
Okay, so actually there is a question online. So wait up, yeah, I check for you first. Okay, so there is views from our reviewer. Your research is a very good commercialized potential finding, especially from oil palm waste. I believe this is from Siti Zaliha. And there is a question for you, Doctor.
Yeah.
Yes, this is from Professor Russo.
Oh, okay. The head of center.
Yes, he asking you. The first question is why the relationship between the surface area and pore size of dope sample is not linearly correlated. And he asks you to please explain a bit more related to how the basicity properties support the surface area and how to determine the basicity properties. So maybe you can go for the first question first, Doctor.
Yeah, hopefully I not forget about
Okay.
the
The
question.
surface and
Uh,
pore size.
how I can see. The first question is regarding the what is it? Why
Relation-
the surface area? Because I
Yes.
cannot see the question.
Yes. The relationship between the surface area and pore size, though it is seen that it is not linearly correlated. Why is
Oh,
that?
okay. All right. I got the point. Rusop asking me why the surface area is not correlated between with the porosity.
Yes.
Yeah, of course, this is a very two different physical observation. The surface area is quite related into the particle size. The smaller the size, the larger the surface area, or the bigger the size, the smaller the surface area. However, okay, the surface area we calculate using the BAT technique. However, the porosity is another dimension of characterization. Is not supposedly directly correlated. It can be opposed or it can be inversely proportional because the porosity will be depending on the synthesis technique. It also depending on the product that we obtain. If we are lucky, our product, the catalyst is a porous type. Uh, we can prove using the BJH technique, but most of the cases, the metal oxide, alkaline metal oxide, and magnesium oxide is macroporous, is or is non-porous most of the cases. But for those you are using the activated carbon, I believe the activated carbon is a normally is a porous material. So I think for my personal point of view, the surface area is not directly proportional to the porosity. Sometimes it can be agreed, in sometimes it can be not agreed. So I think maybe Professor can understand what I say. What is the second question, Dr. Ini?
Okay. So
The
I hope
basicity.
yes. The second question, he asks you to explain a bit more related to how the basicity properties would support the surface area and how to determine the basicity properties.
Okay. Uh, All right. We hope, of course, in catalysis research, we will design two different catalysts, either acidic catalyst or a basic catalyst. It's depending on the reaction. So now, because I'm looking for the hydrogen reaction, the hydrogen is the product. The catalyst is supposedly is a basic initial, so it's not acidic. So in order for us to have a higher amount of basicity, we need very small particle size, particle size to produce higher amount of basicity. Okay, so the basicity contributed in this study, the basicity is come from the active metal. It's not only the active metal, the nickel, the zinc, but the magnesium oxide is a basic enough. Okay, we know the alkaline metal oxide, the calcium oxide, the magnesium oxide is and also base metal oxide. So how do I relate the basicity on the catalytic performance? According to the literature, as I mentioned just now, the promoting the water-Gibbs reaction, we need a basic catalyst. It's not acidic catalyst. If the acidic catalyst, the water-Gibbs reaction is not activated. So the basic catalyst will promote the water gas shift reaction. It provides the reaction medium for the carbon monoxide to react with the reaction medium, the water, in order to boosting to elevate the yield of the hydrogen. Okay, another question, Dr. Ini?
Okay, Dr. Sufri, the time is very big to us, basically. So
Okay.
there is no other question, but I have a question for you because I'm very interested on the yes, the biomass thing, the front. Where did you get all those points, Dr. Sufri? Did you make a collaboration with yeah, maybe palm oil company or whatsoever?
Oh, okay, this one. The biomass that I use in this study, the OPF biomass, where I
Yes.
find it out. Okay,
Okay.
during my PhD duration study, I just go to any kebun or the plantation. During that time I went to the Putrajaya, nearby a plantation in Putrajaya. I just go and collect the dry OPF that are fallen from the tree, and then I just do the processing, cut it off, do the sieving, chop it. Yeah, I do it by myself. I
Oh,
not obtain from any supplier. I just go to the kebun, the plantation, and then collect by myself. Yeah.
okay. So maybe for your future collaboration, to yes, to approve any palm oil company, since
Okay.
now
Unfortunately,
really
yeah.
looking forward on the collaboration things.
Yeah, of course. I think the potential of hydrogen is the fuel is yeah, is a good potential, but unfortunately I couldn't carry out the gasification reaction in my lab at the Institute of Science. So it's hardly sadly to say. So I stopped the gasification reaction because I don't have the reactor in order to convert the gasification, to convert the product into the hydrogen. But I believe some of the researcher from the engineering, the chemical engineering, some of them are actively in the gasification. Maybe, yeah, maybe I can join them or they can join me because my specialist on the catalysis area instead of the biofuel. Biofuel is the application of it. So
Oh,
of course, I'm looking forward to the future collaboration from the ini industry. One collaborator from Sirim in the section 2. Inshallah, they are focusing on the Syngas is the biofuel. I can visit the lab and see how to match the research interest between me and in the researcher. Okay. Yeah.
okay. Okay, I think that's all for today, Dr. Sufri. So no other question. Because maybe you have explained all very fair and clear to all of us. So uh, I wish you good luck
Thank you.
in the research, especially. On behalf of the TNCPI, I would like to thank you very much especially to you, Dr. Sufri, and to all the viewers for spending the time this Friday evening. And again, have time together again in the near future, hopefully.
Yes,
So
sure can.
thank you very much to all. Yes, thank you very
Okay.
much to all. Assalamualaikum warahmatullahi wabarakatuh. Bye bye, everyone.
Okay. Bye bye, everyone. Thank you for the audience. Bye. Assalamualaikum.
Waalaikumsalam.